All right, so in this second video, I'm going to set up the chart, and I wanted to talk to you about the intervals that we would be using. So this is a rational function, and so we can begin at negative infinity, and you just want to be sure that you are keeping track of all of your different breaks. So on the far left, we have negative infinity, and then the next break would be the -3 times the square root of 3. And that was one of your critical numbers from f prime. And then we'll look at what's going on at x equals -3 square root 3. Now notice that I had the advantage of knowing how many rows to go ahead and type in for you, but you'll have to kind of count that out for yourself. Then our next interval will go from -3 square root 3 to -3. And then we'll look and see what's happening at x equals -3. And actually, we already know this, so I would encourage you to put that this is where f prime is undefined, also where f double prime is undefined, because the characteristic is that we have a vertical asymptote here at x equals -3. And then we'll keep moving on from here. So we'll go from -3 to our next break, which would be the critical number or possible point of inflection of 0. And so we'll look at what happens at x equals 0. Then we'll go from 0 to 3 as the next interval, and look at what happens at x equals 3. Now this is our other vertical asymptote, so you could say that your f prime is undefined along with f double prime, and you've got a vertical asymptote at x equals 3. And then we'll go from 3 and then 3 square root 3 as our next interval. We'll look at what's happening at x equals 3 square root 3. Again, that was a critical number from your first derivative. And finally, from 3 square root 3 onto infinity. So those are the established intervals that we have based on the possible points of inflection, the critical numbers, and the vertical asymptotes. That's how you establish the intervals. So now we'll look at f prime in each one of these intervals. And I'm just going to talk us through this without having us actually show the work. So negative infinity to -3 square root 3. And again, you will be thinking of a number in that interval, and you're going to be substituting that into f prime. The version of f prime that I would use this time is the one with the parentheses. So for example, the negative infinity to -3 square root 3. Now, I don't have a calculator up, but I definitely know a number like -100 would be in that interval. So if I took -100 and squared that, and then took -100 squared minus 27, and then divided that by my denominator, which no matter what x is squared. My denominator is going to be positive, this is going to be positive, and this is going to be positive. So that whole expression is positive. So I don't need to know the numerical value. I just need to reason through, is that going to be positive or negative? So I have a positive number for f prime in the interval from negative infinity to negative 3 square root 3. And then because this was a critical number, I know my f prime was a 0. Now, this one would be a little more difficult. I would probably need to get a decimal to know what to use between negative 3 square root 3 and negative 3. So if you need to, you can always switch that out. Negative 3 square root 3, you can figure out what that is as a decimal. I do know that it is that negative 4 would work in that interval. So if I put negative 4 into the first derivative, I'm going to find out that I have a negative. If I go from negative 3 to 0, I could use negative 2 as my number. Plugging that into the first derivative, I'll get a negative. At 0 to 3, I could use 1. Plugging 1 into the first derivative, I get a negative. I could use positive 4 for my next interval. I'm going to get a negative. At 3 square root 3, that was a critical number, and so the first derivative is a 0. And then from 3 square root 3 on to infinity, I could use a big number there, and I'll find out that my first derivative is positive. So I have f prime considered. Now I'm going to look at f double prime. For f double prime, to do my calculations, I would use this version of f double prime. So, for example, I'm going to use negative 100 again. If I take 18 times negative 100, and then take negative 100 squared, and then add 27, and then divide by my denominator, and my denominator is x squared minus 9, so negative 100 squared minus 9, all of that to the third power. Well, this multiplication is going to be a negative. This, I'm squaring 100 and adding 27, that's going to be positive. Here I'm squaring 100 and subtracting 9, that's going to be a positive. So in this fraction, I have a negative times a positive times or over a positive. That's going to make my fraction be a negative, and therefore f double prime for that section will be a negative. So that's the work that you need to be thinking about as you're going through and doing your second derivative. And so on your second derivative, from negative 3 square root 3 to negative 3, that is also going to be a negative if you use negative 4 in there. From negative 3 to 0, if we use negative 2, actually you'll find that your second derivative is positive. At 0, we got 0, and you could also fill in 0. It was a critical number. You could fill that in for the f prime as well. From 0 to 3, we could use 1, and you would find that your second derivative is negative. And then from 3 to 3 square root 3, we could use 4. We'll find out that we have a positive. And then from 3 square root 3 on, so you could use 100 again, you'll find out that you have a positive. second derivative. So you'll have to do your numerical analysis of f prime and f double prime. And then based on those two analyses, you can now do your characteristics. So since f prime is positive, we know that f is increasing. Since f double prime is negative, we know that the graph is concave down. So increasing and concave down. And then we'll take a look at the next interval. It's negative for f prime. So that means that we have a decreasing graph. And that will have a negative second derivative, so remaining concave down. So let's go ahead and look at what happens since we had this change from increasing to decreasing. That means that at x equals 0, we have a relative maximum. And I left you with another column because I want the ordered pair. So the ordered pair would be negative 3 square root of 3. And then you would need to substitute that negative 3 square root 3 into the original problem. So be sure that you substitute it into f. And in so doing, you would get negative 9 square root 3 over 2. And that would be your ordered pair that is the relative maximum. At x equals negative 3, we had that vertical asymptote. So we can go on and look at what's happening at the interval from negative 3 to 0. We still have the graph decreasing, but we have a change to concave up. So the graph is concave up. Then we have x equals 0. The graph stays decreasing. So that lets us know that although 0 was a critical number, it does not produce a maximum or a minimum. But we do have a change from concave up to concave down. And so that makes the 0 be a point of inflection. We went from concave up to concave down. We can plug 0 into the original problem. Make sure you plug it into f, and you will get a 0 for the y value. All right, and then we have your vertical asymptote. We'll look at f prime being negative, so continuing to decrease, and then we have concave up. Now notice that even though I have a change from concave down to concave up, because I have a vertical asymptote, I do not have a point of inflection. All right, and then our last analysis, f prime is positive, so we have a change to increasing. The graph remains concave up. So since we're changing from decreasing to increasing, that means that we have a relative minimum. So at x equals 3 square root 3, we have a relative min. And so you have 3 square root 3 as your x, and then your y. It happens to be symmetrical, so 9 square root 3 over 2. And there is your table. So now we're going to take that information and draw the graph. So I moved my graph so that we could see it while having the table on the screen as well. Now, I did not really give you a big enough graph to handle the 3 square root 3 and the 9 square root 3 over 2. So we'll have to go off the graph just a little bit, but I think you'll be fine. So when you're graphing, wait a minute. Before we graph, I want to fill in the blanks over here. So your relative maximum would be negative 3 square root 3, and then negative 9 square root 3 over 2. I'm sorry, that is your relative minimum. This is your maximum. So we'll use the positives for that. So 3 square root 3 and 9 square root 3 over 2. And then for this one, negative 3 square root 3 and negative 9 square root 3 over 2. No, I had that right. This is negative 3 square root 3 and negative 9 square root 3 over 2. That was a relative maximum. And then 3 square root 3 and 9 square root 3 over 2. So even though the signs don't make sense when you see the graph, you'll see it. Trust what your table says. So maximum negative 3 square root 3 and negative 9 square root 3 over 2. And then the minimum 3 square root 3 and 9 square root 3 over 2. And then your point of inflection, and we just had the 1, and that would be at 0, 0. So now we're ready to draw the graph. Of course, you'll want to place the X and Y axis. Try to get there in the middle. And you may have to extend it some. So you want to plot any points that you possibly can. For example, the X and Y intercept were both 0, 0. So you definitely want to plot that point. We will also be plotting the maxes and mins, but I want to get the vertical asymptotes on first. So you had 1 at x equals 3. You had 1 at x equals negative 3. And you have a slant asymptote of y equals x. That will start at 0, 0 and go up 1, right 1. And up 1, right 1. So you've got a slant asymptote. And be careful drawing this, that you stay in line. So those are the 3 asymptotes that you have. All right. I want to plot now our first point, which is a relative maximum. Now it's negative 3 square root 3 and negative 9 square root 3 over 2. So the decimals for those, I have the decimal values. So I'm going to write those off to the side here for us. Negative 3 square root 3 has a decimal value of negative 5.2. And negative 9 square root 3 over 2 has a decimal value of negative 7.8. Both of those are approximations. So as we plot that ordered pair. You can see I did not give us enough room, so you're going to have to estimate. So this is -3, -4, -5.2 is going to be just to the left of the -5, and then down at -7.8. So 1, 2, 3, 4, 5, 6, 7. So roughly about right in here is going to be that relative maximum. And so let's think about what's going on. It says that we are increasing and concave down. So we need a graph that follows that slant asymptote and increases. So starts low, goes high, hits the relative maximum, and stays concave down, and then goes toward the x equals -3 vertical asymptote. So there's one portion of the graph. And even though I was a little hesitant, that is a relative maximum at -3 square root 3 and -9 square root 3 over 2. Then after the vertical asymptote, we have the graph being decreasing, concave up, and then we hit a point of inflection. So the graph is going to be decreasing. So after the vertical asymptote, we have to hit 0, 0, but that means we're going to be starting high and hitting 0, 0. So along the vertical asymptote, and we have to be concave up. So concave up, hitting the vertical asymptote, and then heading towards 0, 0. But at 0, 0, it switches to concave down because we have a point of inflection. So concave down, we're going to continue to decrease until we get to that other vertical asymptote. So continue to decrease, concave down. So you should see your graph being concave up and then concave down, changing concavity at 0, 0. And then finally, we have one more point to plot. It's the +3 square root 3. So positive 5.2 and positive 7.8. So we're roughly about in this spot. And this is going to be a relative minimum. So I'm going to erase this right here just to make it easier for us to concentrate. So this is a relative minimum. Remember, we're starting at x equals 3, the vertical asymptote. It says we need to decrease. So we want to start high and move low. We need to be concave up. So starting along that vertical asymptote, heading toward the relative minimum, concave up. We stay concave up, and we follow that slant asymptote with our relative minimum at +3 square root 3 and 9 square root 3 over 2. And that would be our graph. It might help to extend the slant asymptote just a little bit more for you to see it, and extend that vertical asymptote and do the same thing on this side as well. So you can see what happens there. So you've got a rational graph. Now, you're going to have to do, I think, 6 or 7 of these, and you can see this takes a lot of time, and you just can't afford mistakes on your first and second derivatives. So take your time. Please do not rely on the calculator to do your graphs, or this is going to be a disaster for you when it comes time for the assessment. So good luck on this. Be sure to ask questions. I'm sure you'll have them along the way.